Shooters, reloaders, and conversationalists, welcome to PounderLabs. We're very fortunate to come across a very unique device called the Internal Concentricity Comparator, often referred to as the Vern Juenke Machine. This is a two-part presentation. In this first video, we want to introduce the ICC device, tell you a little bit about the inventor Vern Juenke, and see if we can help demystify some of what this device does. In a second video, we do a hands-on walkthrough testing various bullets. We'd also like to ask any users that have one of these, feel free to comment to the videos and post any links and share any experiences, because it's our observation this might be some of the first videos that show up about this very interesting device, and we'd hate to see it get lost in time and tide. The ICC is an instrument to measure the wall concentricity of jacketed bullets. It was designed and built by Vern Juenke. There have been many revisions over several decades, and it's likely, like many of us, he gained experience with this method on the job or a project. And Mr. Juenke passed away in 2018. It uses the eddy current induction method. This is an established non-destructive testing technique broadly used in industry. It might seem like a magical thing to some, but it's just science, and we'll explain. It's a very sensitive to small deviations, down in the thousands to a tenth of a thousandth range, and the theory of operation is solid, and it's a great application for testing jacketed bullets. Actually, in our experience, totally unique in the industry. Eddy currents are part of the study of electromagnetism. Basically, they're current flow in conductive materials that are created by induction. Michael Faraday was credited with first identifying induction in early 1830s, and independently J. Henry also identified the technique about years later. In about 1834, Lenz put down a very important guideline called the Lenz law that says that these fields that get created from the currents counterflow the magnetic fields that created them. So this is where all the manner of dynamic braking and everything are based on. Around September of 1855, the stage is set now for a French physicist named Foucault to identify and is credited with the discovery of eddy currents. You might recognize the name with the Foucault pendulum seen around the world to demonstrate the movement of the planet Earth, and he's also credited with naming the gyroscope. Here's the basic theory of operation for eddy current testing. The alternating voltage current goes through a coil, creating the magnetic field, this primary field, and then by induction, this field creates current flows in the conductive material from the secondary fields created. And these are what's called eddy currents because they look like currents of flow in water. And when flaws are detected in these flows, a coil in the instrument detects the change, the signals process, and this change is displayed as units of deviation. A couple of really important things. One is this liftoff. This is the gap between, let's say, the surface of the sample, or in this case, like the bullet jacket, and the actual sensor itself. Second thing is also the depth of penetration. So these have to be designed into the item that's being tested and varies with the type of testing being done. Here's non-destructive testing being done on a piece of material here. Here's what a device looks like. An interesting takeoff of this is that how you can test paint film. So the substrate is here and the probe comes down, sits on top of the paint film. The fact that this liftoff changes the size of the field, you're actually able to calibrate this and measure the depth or the thickness of paint coatings. A variety of flaws can be detected in the jackets of the bullets. If we look at cross sections here, can be cracks. Also, the lead core can be off center with the jacket of the bullet. There's a couple of variations of ovoid. The lead core could be very well made, but the jacket itself isn't consistent around there. And then also the lead core could be oval, and that ends up creating a variation in the wall thickness of the jacket going around that core. Also, though, there's kind of a byproduct. Of this measurement is what we call egg shape. In this case here, the lead core and the jacket are both not round. And what will happen as this rotates, because the change is happening in the liftoff, you'll get a detection of a flaw. So although it's not a flaw like these here, it's still something that'll affect the performance of the bullet and something you'd want to know about. Here's a few things around limitations and techniques. Here's a close-up of the test fixture so you can see the bullet mounted and ready for testing here. Keep in mind this is for jacketed bullets only. You must have a conductive alloy, which in our case is pretty much copper alloys. It's not designed for monometal bullets. You can see that the bearing surface rotates on these ball bearings, so there's kind of a minimum length. You can go down to 223, probably things greater than 55 grain. You can go up to about 0.34 inch, and say 8 millimeter would be covered. So you can test a very broad range of bullets very easily. Couple of guidelines: don't run it on cantilures like you see this bullet here. If there's a guideline or a crimp cantilever up here not interfering with the bearing surface, you're probably good to go. But if that cantilever sits in the rotation part, it's not a good thing. Also, the system won't handle the big 50 BMG bullets. It's just too large, creating too much lift off in the mechanism. Now remember, that doesn't do anything in terms of indicating lead cores, or not even sure you get any insights on the core jacket bonding. It's important that, as you can see, this needs to run on the bearing surface. So it's best with a given bullet positioned the same. So we think in-lot or lot-to-lot testing is the best area to apply this. You'll get different ranges of deviation for different calipers, so keeping them all within the same family is probably a good technique. Now that you've learned a little bit about it, hopefully you'll agree with us that the Vern Juenke Machine is indeed an amazing device. Short learning curve, valuable insights. This grew out of the bench rest disciplines, but with all the interest in long range and extreme long range shooting today, it might be a good idea to take a good hard look at the quality of our bullets, and this device can help with that. I would like to thank Joel Pendergraph with Pendergraph Gunwork for making the Juenke available to us. We'll leave it to the viewer for additional studies about availability, a couple of other sites that you might want to visit, and then you can visit our Facebook page or the PounderLabs YouTube channel for more videos from us. We'd like to dedicate this work to Joel's good friend Charles, who's a gentleman shooter, innovator, and the owner of the Juenke device we're demonstrating today. This completes our presentation, and as you're thinking about subscribing, please look over these important notes and disclaimers. They're here for your safety and ours. Thanks for watching. Be safe. See you soon.